This is a simulation of an airfoil flying through atmospheric air at cruise conditions, modeled in ANSYS Fluent. This is a common type of model used in aerospace engineering design. It's a good tool to help understand the aerodynamic properties of lift as well as drag as it relates to airplane wings, propellers, and more. This is a simulation that any aerospace engineer who hopes to go into aeronautical design will need to know. It's one that I use very frequently in my research lab, and today I'm going to show you how to run one.
The first thing we need to do is actually get our airfoil. What that means is we have to find a coordinate file for the airfoil that we're going to plot. I'll show you how to do all of that here in just a minute, but the first thing we need to do is get the coordinates for the airfoil that we're going to be modeling in the simulation. So to do that, we need to go find a coordinate file for the airfoil. Now, a really fantastic resource for airfoil coordinate files is this website right here. You can actually use this section right here to make your own airfoil. You can change things like the max camber. You can make it all the way up here and it winds up with a much more curved over airfoil, or you can bring it back down. You can make more points on the airfoil to make a more refined line from the plots given. You can make the airfoil thinner, make it really thin like this. This would be for more of a high-speed airfoil, like one you would see on the delta wing of the Concorde or something like that. Another thing is you can change where this camber is. What the camber is the part of the airfoil that curves upwards. You have this coming down here on the underside of the airfoil, and the camber is this upwards curve that develops towards the rear of the airfoil. But you can move it way up front if you want, like this. You can move it way to the back, usually right around the middle is common airfoil shape. You can also use airfoils already developed from research by NACA. The airfoil I'm going to use for this video is NACA 4412. It's a good airfoil shape, it produces a decent amount of lift, and it's a pretty commonly used airfoil. To get this, we need to start by copying all the coordinates here, and you want to paste them into an Excel file just like this. You might have to play around with the way that this pastes into the Excel sheet, and you definitely need to add X, Y, and Z coordinates to this, so label X, Y, and Z, and the final coordinate file should look like this. The reason we need a Z coordinate column, even though the entire column is populated with zeros, is because ANSYS simulates three-dimensional space. So if we have a perfectly two-dimensional object, we still need to denote that every single point is at the 0 point on the Z-axis. So add an extra column for Z, mark it down to 0. And then we also need to label columns just like this, and then we have our coordinates exactly the way they need to be. But before we can upload this into ANSYS, we need to copy these into two text files. The reason we need two is because when we bring in coordinates into ANSYS to make the curve that's going to produce this airfoil, ANSYS won't produce a curve that overlaps itself. So we have to use from the top down to where it hits 0 to make the top curve of the airfoil, and then from 0 down the end to make the bottom curve of the airfoil. The reason we're using 0 twice is because this makes sure that the two curves we make in ANSYS touch each other. That way when we go to make a surface out of the edges, we have a fully enclosed region made by those curves to make a surface. Now that we have all of our coordinates here ready to go, all we need to do is upload these into a text file. To do that, we copy from the first coordinate through the 0 into our first notepad file. And then we save this as the airfoil top. Then we do the same thing, except now we start from 0 and go to the last coordinate. Copy this, open up Notepad, and paste our coordinates into Notepad. When you do paste the coordinates in, you might need to move the numbers around just so that they all line up vertically in good columns. For this file, all the coordinates are lined up exactly how we need them, so we don't need to do any editing like that. And that's it. Now we have our coordinates ready to go. We just need to open up ANSYS and get started with the simulation. So now we have ANSYS Workbench student version opened up. If you don't have ANSYS and you don't know how to get it, go ahead and click the video you see right here, or follow the link in the description for a full tutorial that I made to show you where and how you can get ANSYS Student on your computer completely for free. Now that we have ANSYS Workbench open, we need to start with the right app. For airflow analysis, we're pretty much always going to use Fluid Flow Fluent. Double click that to open it, then right click and click New Design Model or Geometry. Now that we have Design Model Geometry open, we can start to build the geometry that we're going to be modeling in the simulation. One of the most important things to know starting a simulation like this is that when we go to model an airfoil, which is the cross section of a wing, we're going to be modeling a two-dimensional plane. What that means is we're only creating a two-dimensional surface, and ANSYS has the power to run a full simulation and find the lift and drag coefficients of our airfoil under cruise conditions that we're setting in here in a two-dimensional surface plane. The second important thing to note before we come into this is that when we model something in ANSYS, the geometry that we're making has to be the thing that we're modeling. If we're modeling a beam, we make a beam. If we're modeling airflow around an airfoil, we make the geometry of the air itself, not the airfoil. That's because in this simulation, we don't care what's happening to the airfoil itself. We care about what's happening to the air around the airfoil. With that in mind, let's get started. The first thing we do is select the XY plane and set our perspective to look straight at it. Then we're going to produce the total shape that's going to be the boundaries of the air that we're modeling. So we go to sketching and start with the rectangle and build a nice large rectangle. Now, if we were making a simulation to predict, let's say, wind tunnel data, we would stop at a rectangle because the wind tunnel volume itself is a rectangular prism that operates under laminar flow. However, we're modeling airflow in the atmosphere. When you're in that situation, the flow is turbulent, and essentially what that means is the air coming at the airfoil is coming in from all directions. To make sure that we model that as accurately as possible, instead of just using a rectangle, we're going to model the front, which will make the inlet boundary for the air coming in to the front of the airfoil with a very large arc coming around the front. So we start with an arc by 3 points. Make sure that this lines up as a P. In ANSYS, if you're lined up with a line, you get a C. If you're lined up with a point, you get a P. We're trying to line up this arc with this rectangle in points, so we line it up at the P, line it up with the other P, and then make sure that these lines line up as best as possible. Then we go to dimensions, and we set the dimensions for this atmosphere simulation. Start with a vertical dimension to set this distance right here, and then a horizontal to set this distance here. And then one last vertical. This way we can make sure the space we're creating is symmetrical at the x-axis. And then set the dimensions. I actually don't want a space this large because this will produce way too many mesh elements when I go to make a fine enough mesh for ANSYS Student to allow me to operate with. So I'm going to make this 20 meters and then each vertical 15. Now that we have the outside boundaries for our airflow, we can go ahead and go to Modify, Trim, and get rid of this line, just because we don't need that when we're going to model the airfoil. Now we go to modeling, and like I was talking about earlier, we need to make this into a two-dimensional surface. So to make one, we go to Concept, Surfaces from Sketches, and select our sketch, and click Apply, and then Generate. And now we have a surface that will be the air that we're going to be producing. But when ANSYS makes an object, it can make an object as a fluid or as a solid, and it defaults solid. We want this to be a fluid. So expand the one part one body, click surface body. Down here where it says fluid solid, click on solid, drop down menu, change it to fluid, and generate. Now we just need to introduce the airfoil. To do that, we click concept, 3D curve, and change this from point selection to coordinate file. Then we go and select the coordinate file that we made earlier. I'm going to start with the top of the airfoil and then click generate. Now we have the curve making the top, and as you can see here, the curve is way down here. This is still a full-size airfoil. So the area of air that we're modeling is plenty to get a pretty accurate determination of the airflow around the airfoil at this point. Then we right-click, form a box to zoom in. Now we can go concept, 3D curve again, and produce the bottom. And again, we select the coordinate file, this time for the bottom of the airfoil. Now when we go to zoom in, we have the outline of a full airfoil. What we need to do now is produce a surface for the airfoil and then use that airfoil surface to cut out the shape of the airfoil from our air surface. That way we're modeling the air with the airfoil essentially in the way. So we go Concept, Surfaces from Edges now because we created a 3D curve, not a sketch. And then Control so that we can select both. Click both edges. Select Apply, and Generate. Now we have a surface to simulate the airfoil that we're going to use to cut out that shape of the airfoil from the air. This airfoil is direct on axis and has an angle of attack of 0. If you want to produce an angle of attack, go Create, select Body Transformation, drop down and go to Rotate. Then we select our airfoil surface body, Apply, And for the axis selection, we need to select the z-axis. So click the ZX plane, change to a three-dimensional point of view so that we can see the z-axis. Click the z-axis, click apply, and then set the angle. A common angle of attack is 5 degrees. Now, since we're rotating it from the origin down, let's do -5 degrees and click generate. Now when we look back at this, we can see this is our original outline of the airfoil, and this is where our airfoil is now that we've set in this angle of attack. We don't have to do this. We can definitely set this as on axis. It's important to note though that most airplane wings do operate on an angle of attack. This way it can maximize the amount of lift it produces while minimizing drag and preventing flow separation. For now we're going to keep this angle of attack, and I'm going to show you at the end of the video what the simulation would look like if we hadn't kept the angle of attack in. The next thing we do is cut this airfoil out of the total surface of air. To do that, we need to create a Boolean. So we go to create, select Boolean, go where it says Operation Unite, click the drop-down menu, and select Subtract. The target body is what we're cutting out from, and that is our air surface. So select that and click Apply. Our tool body is what we're using to cut out, and that's our airfoil surface. It's already selected, now we click Apply. Then Generate. Now we can see that the shape of the airfoil is completely cut out from the air surface. Now when we model the air as a moving fluid, you'll be forced to move around this shape. Okay, so now that our geometry is finished, we need to go and produce the mesh that's going to be used in the analysis of this airflow. Now that we have the geometry set, we can go right here to Mesh, right-click, Update. You always want to update the new tab before you go to edit. That way, the geometry in this case ports over into the Mesh tab, so we actually have the right geometry to mesh when we go to do this. When we go to do setup, we're going to do the exact same thing. That way, the mesh and the geometry pour it into setup so that we're modeling the right piece. Now that the mesh is updated, we go right click, edit. Now I have the mesh open. We just need to set up the right perspective. And we're set. Let's go ahead and click mesh. Now for anyone watching who has never used ANSYS before, probably exactly like I did when I was starting out here, you have no idea what you're looking at here. This is a collection of elements, that's all these squares, that make up the total of the part that we are analyzing. What each of these represents is a single data point in a string of differential equations that the ANSYS modeling software is going to use to run the simulation that we're going to be running. What that means is when we zoom in here to the airfoil, we don't actually have all that many data points along the line of the airfoil in certain spots along here, and that's something we need to change. We need as fine of a mesh or as many data points per unit of area as we can get away with, because that will give us as accurate and as useful of data as possible. To do that, we go over here, go to element size, and go, instead of the default, which is over 2 meters, set this at 100 millimeters or 0.1 meters and click generate. Now we've got the mesh complete and we can go ahead and zoom in to the airfoil. That's a lot better. We've got more than double the number of elements along the airfoil. So this is going to give us much more refined data when we go to run the airflow simulation here. But before we do that, we need to define our inlet and our outlet. What that means is if we're treating this as a space that air is flowing into, this curve here is our inlet and this flat line out here is our outlet. To do that, we need to do what's called creating named selection. Go to Edge Select, first click it, and then right-click, create named selection, call that inlet, and then do the exact same thing for the outlet. Click OK, and then click Generate. And now we can see our named selections are showing up here. So we're finished meshing, and now we can go over to setting up the actual simulation.
Now that the geometry and the mesh are both completely done, we can go into actually setting up the Fluent simulation. You right-click Setup, and click Edit. Then you'll see this Fluid Launcher tab set up. These settings are already what we need for the simulation that we're about to do. So click Start. When we pull up Setup, this is what it should look like. The name selections that we made in our mesh are coming through as our inlet with all the arrows pointing in and our outlet with all the arrows pointing out. So now we're going to go to this tree and go top to bottom. Starting with models, we need everything here to be off except for viscous, where we want this to be set as K epsilon 2 equation with standard wall functions. Select OK. Then we're done with models. We want to go to materials, fluid, check the properties and make sure that is what we need. Don't bother with solid because we aren't making a solid. Then cell zone conditions, fluid, just make sure that the surface body here is what's being considered our fluid, and it is, so we're good there. Then boundary conditions. This is where things get especially important. Starting with our inlet, that's again this section of the blue arrows. Inlet velocity inlet. So we come in here and we're going to set our velocity. Reference frame is absolute, magnitude normal to boundary. That's exactly what we want. Then we need to put in the velocity. I'm going to look up the cruise speed of a 737 and use that. So we see here the cruise speed is 828 kilometers per hour. To convert this to meters per second, just multiply by 1,000 and then divide by 3,600 so that kilometers becomes meters and your hours become seconds. And when you do that math, it comes out to 230 meters per second. We're going to set that in there. Gauge pressure should be 0 because this is going to be at atmospheric pressure. Gauge pressure means the difference between your pressure and atmospheric pressure. So that's exactly what we want, and everything else can say exactly how it is. Apply and close. Then we go to outlet, pressure outlet, and again, gauge pressure 0. Pressure profile multiplier 1, normal to boundary, total pressure. Exactly what we want. Then internal surface body, make sure it's the right one. Apply, close. Then with wall, we open it up, and this is a stationary wall with no slip conditions. What that means is our wall is our airfoil lines. And no slip condition means the air is flowing across the surface without any slippage, which means if you imagined it as a wheel moving across the ground, like assuming the wheel continues to roll rather than slipping and sliding. So this is how we want it. Apply and close. Now we're done with boundary conditions. We now go to report definitions, click new, force report. We're going to put in a drag and a lift coefficient report definition. That way when we're done with the simulation, we'll have a graph of the drag and lift coefficients. So start with drag coefficient, wall surface body, and then another new one for force, lift coefficient, wall surface body, and click OK. So now we have our report definitions, lift coefficient and drag coefficient, so we're good there. Then double click initialization, make sure it's at hybrid initialization, and initialize. Now that the initialization is done, double click run calculation under calculation activities. Here the only thing we need to change is the number of iterations, and I'm going to set this at 1,000 iteration. An iteration is just a new time calculating, so that way when we have our graphs showing our data, even our contours as well, we'll have more data points to work with. But more importantly, it's going to be a more reliable calculation because it'll run through the scenario time after time after time after time, so that our data is going to come through and be statistically significant. Now that we have a decent number of iterations for our calculation, all we have to do is click calculate and sit back and wait for it to load. And this is actually really cool. ANSYS will show you in real time the graphs that we defined earlier, developing and generating points. So you can see that for the lift coefficient as well as for the drag coefficient. Now our calculation is done. We can look at the drag coefficient as well as the lift coefficient, and as you can see, both of them eventually settle on a single value as the iterations go on. This is another reason why we need to do so many iterations through something like this, so we can make sure we're actually using the right values when we're making our design decisions. So next, go to graphics and click contours, and we're going to add velocity and pressure contours. This way we can see visually what's actually happening with the airflow here, and that can help us understand the interaction going on between the airfoil and the air that's producing the lift that we're seeing in the data here. So now I have our pressure contour built. We're using the interior surface body, and we're setting it as smooth coloring. As you can see, the coloring goes across the spectrum from blue to red. The more to blue it is, the lower the pressure is, the more to red, the higher the pressure. The total surface of air from left to right goes from red to blue because the air is flowing from left to right, and air will always flow from high to low pressure. So that is nothing new. When we zoom into the airfoil though, this is where it really matters. When a wing is flying through the air, the thing that produces lift isn't just on the bottom of the surface, air is coming in and then bouncing off at an angle and pushing it up. That does play a role in this, which is why we have the angle of attack. But fundamentally, and even that is built on this concept here, what's really happening is you have higher pressure air below and lower pressure air above the wing. That's producing a sort of suction effect where the high pressure air is trying to push the wing up and the low pressure air is providing a space for the wing to naturally be able to move into. It's the same principle that vacuum cleaners operate on, really. It's a suction that's pulling this up. And that's produced by this difference in length along the top versus bottom of the airfoil. When the air is flowing across the shorter length, it flows at the speed that the air was flowing at. But when it flows across the higher length, it flows faster. And the reason it flows faster is because if you're to consider this a control volume, due to the law of conservation of mass, the flow of mass or the flow of volume of the air on either side of this has to be the same, because the rate of mass flow right here at the front of the airfoil has to be the same as at the back of the airfoil. But the air across the top of the airfoil has more room to cover in the same amount of time versus the air at the bottom of the airfoil. So it's going to be moving faster. And when it moves faster, because the mass flow rate has to stay the same. You can't have more air flowing. So when the air is moving faster, it becomes more stretched out across that further distance, thus producing lower density and lower pressure as a result. So that's actually what the shape of an airfoil is entirely designed to do, is produce this pressure difference between the top and bottom of the airfoil and produce that suction effect that we call lift. So that's our pressure contour. Now we make a velocity contour doing essentially the same thing except setting it to velocity and velocity magnitude, still for surface body, compute, save and display, close. And now we can zoom in and see exactly what I was talking about just now for the velocity values that is producing that pressure difference. So we have clearly higher values at red and lower values at blue, much faster airflow rate above the airfoil versus below, and that's what's producing that pressure difference. Another thing we see is a slower velocity along the surface of the airfoil. That's because what's happening here is we're producing a boundary layer of airflow where the velocity is actually slowing down ultimately to zero at the surface of the airfoil. That happens anytime there's air interaction with a solid surface. There's going to be a boundary layer. And so one of the things that we actually do in aerospace engineering when designing planes for better performance is finding ways to reduce the thickness of the boundary layer that develops around an airframe. That way we reduce the amount of air that's slowing down, and in doing so we can reduce the drag. So here, this is a little bit exaggerated. The boundary layer isn't going to actually be this thick, otherwise we would have flow separation here. But this is a good picture representation of what's going on. We can also see this change in velocity that carries on and trails behind the trailing edge of that airfoil. And this is what a simulation looks like without the angle of attack, like I was talking about earlier. You zoom in and you can still see the low pressure up top, but the pressure underneath isn't quite as high, just because the bottom of the airfoil isn't coming in and smacking straight into the airflow like it is when we have that angle of attack. Plus, our leading edge pressure looks a little bit higher relative to the rest of the pressure. This could produce more drag as well. But we still have our pressure difference, which would still produce lift. And as you can see here, we do still have a decent lift coefficient, but it isn't as high as what we had last time with the angle of attack. So that's why most planes will typically have an angle of attack, usually between 2 and 5 degrees. If you get too high of an angle of attack, then you completely negate the effect of the airfoil shape in the first place. Producing that angle of attack just produces a little bit more lift, a little bit more pressure difference between the bottom and the top of the airfoil, and producing more lift as a result. Here we can see as well the velocity contour. Again, we still have decent high velocity across the top of the airfoil, but we don't have the same lower velocity across the bottom with the same level of contrast as we did when we had an angle of attack earlier. And that is how we produce an airfoil analysis simulation in ANSYS Fluent. If you're interested in more content like this, follow the playlist that I've made for videos that I'll be making just like this one. And if you're interested broadly in what I do as a mechanical engineering student getting ready to go into the workforce, go ahead and subscribe to this channel. Thank you for watching.